A long-term study in New South Wales exposed a critical threshold for soil health. When copper concentrations exceed 200 milligrams per kilogram, soil functionality drops significantly, even 12 years after exposure, while electroculture enthusiasts focus on the potential for tripled harvests and deeper green leaves. This data points to a silent crisis occurring underground. High copper levels result in lower beta diversity across plots. This metric reveals a dangerous shift toward biological uniformity, where the variation between different soil ecosystems vanishes and the complex community essential for resilience begins to collapse. To determine if the reward justifies the risk, we must rigorously analyze the theory, the mechanism, the installation, and the environmental fallout. It all begins far removed from the furrowed rows of modern agronomy, within the experimental laboratories of early 20th century physics. The foundational principles driving electroculture do not rely on nitrogen fixation or chemical hydrolysis, but rather on the manipulation of invisible wavelengths. French agricultural engineer Georges Lakhovsky was the first to rigorously propose that biological entities function as minute, self-sustaining oscillating circuits. In his seminal work, he argued that plants, with their extensive physical structures, act essentially as organic antennas, much like a radio receiver tuned to a specific broadcast. He theorized that these organisms are capable of absorbing and utilizing ambient electromagnetic energy to sustain their vitality. According to this theoretical framework, a healthy plant maintains a robust connection to this energy field, while a weakened organism suffers from a dampening of this vital resonance. Lakhovsky posited that conductive materials like copper could amplify this natural process. The atmosphere is not merely empty space. It is a field of ambient electromagnetic energy. The central premise of the antenna theory is that specific copper geometries can capture and focus these ambient frequencies, directing them into the soil to reinforce the natural oscillation of the plant's cellular structure. This narrative bridges the significant gap between vintage oscillation theories and contemporary agricultural applications. Technicians employing this method utilize copper coils, not as structural supports, but as passive waveguides. The copper acts as a highly conductive medium designed to channel specific wavelengths of the electromagnetic spectrum directly into the root zone. Proponents argue that when this channeled energy interacts with the biological circuit of the plant, it acts as a supplementary energy source. This external energetic input ostensibly stimulates cellular activity, fostering more robust growth without the need for synthetic hormones. Dr. Andrew Goldsworthy, a biotechnologist from Imperial College London, later provided a more contemporary scientific perspective to support these claims. His research indicates that plants have evolved specific biological responses to natural electrical phenomena, such as the shifts in electrical potential that precede heavy rainfall and thunderstorms. Goldsworthy's work suggests that plants are inherently receptive to electrical stimuli, having adapted to detect these environmental cues. The installation of copper antennas is theorized to mimic these natural electrical conditions artificially. By creating a permanent vertical link between the sky and the soil, the copper wire is believed to stimulate these inherent reception pathways, effectively activating a growth response even under clear skies. The physics behind this relies on the conductivity of copper to bridge the potential difference between the atmosphere and the earth. While the air often acts as an insulator, preventing atmospheric charge from flowing freely to the ground, a vertical copper wire offers a path of least resistance. This connection facilitates the passive collection of ambient electrical energy, allowing it to flow down into the earth. This theoretical foundation explains the persistence of the technique despite skepticism from mainstream chemical agriculture. It establishes the primary claim that specific, conductive architecture can harness natural electromagnetic fields. By grounding this atmospheric charge, the copper wire acts as a conduit, effectively functioning as a localized energy source for the soil microbiome and the plant root system. The objective is to supplement material inputs with the energetic inputs of the atmospheric gradient. However, the impact of this energy extends beyond simple absorption. It reportedly triggers a cascade of internal biological changes that fundamentally alter how the plant processes nutrients. The physiological argument for this technique centers on the stimulation of distinct internal metabolic pathways. Proponents hypothesize that the low-voltage stimulation provided by the copper antenna does not merely exist around the plant, but actively accelerates the photosynthetic process itself. At the leaf surface, the mechanism is believed to influence the mechanical behavior of stomata, the microscopic pores responsible for regulating gas exchange. Under standard conditions, these pores open and close in response to direct fluctuations in light and humidity, a process controlled by the swelling and shrinking of guard cells. However, the theory suggests that the introduction of a constant, low-level electrical field enhances the turgor pressure within these guard cells, forcing the stomata to widen significantly beyond their typical range. This proposed dilation would allow for a massive volume of carbon dioxide to enter the leaf structure, removing the primary bottleneck for biomass production. With increased gas exchange rates, the plant could theoretically convert light energy into chemical energy with greater efficiency, effectively supercharging the manufacturing of sugars and starches. Simultaneously, the influence of this electrical field is believed to penetrate the soil surface to alter the fundamental polarity of the root cells. In a neutral state, a root hair must expend significant biological energy to transport mineral ions against a concentration gradient. The electroculture protocol aims to modify this electrochemical environment, creating a polarization that acts like a magnetic pull on specific elements within the soil matrix. This polarization ostensibly improves the uptake of paramagnetic nutrients, specifically iron and zinc, which are highly sensitive to magnetic fields. These elements are often present in the soil, but remain chemically locked or inaccessible to the root system due to weak ionization. By intensifying the electrical potential at the root tip, the hypothesis suggests the plant can attract and absorb these metallic ions more readily. This functionality is considered crucial, as iron serves as a central component in the synthesis of chlorophyll, the pigment vital for photosynthesis. Observations of a deeper green tint in treated plants are frequently cited in field reports, not merely as an aesthetic change, but as visual evidence of this increased photosynthetic efficiency and denser chlorophyll concentration. Beyond the intake of raw materials, the hypothesis suggests that copper facilitates the transport of organic nutrients through the phloem, the vascular tissue responsible for transporting organic nutrients. Copper itself is a highly conductive material, and its presence in the system is believed to facilitate the rapid movement of fluids and metabolic signals. This aligns with the broader claim that the system optimizes the translocation of nutrients from the leaves to the fruit or tuber. The copper coil, functioning as an antenna, absorbs ambient electromagnetic energy and channels it into the plant's biological circuitry, theoretically reducing the resistance against which sap must flow. However, the precise biological pathway for converting these weak magnetic fields into tangible biomass remains largely theoretical. While the widening of stomata and the attraction of paramagnetic salts offer a plausible mechanical explanation, the translation of microvolts into kilogram yields lacks a fully mapped molecular schematic. The scientific community emphasizes that while the components of the theory, principles, the direct causal link between a copper spiral and exponential growth requires further rigorous, controlled investigation to move from hypothesis. The current understanding relies on the premise that the plant is an electrical machine as much as a chemical one, capable of utilizing the potential difference between sky and soil to drive its internal engines. Translating this theoretical potential into a functional agricultural protocol requires a standardized approach to material selection and system geometry. The transition from abstract physics to field application demands precision, as the casual application of scrap metal differs significantly from the rigorous electroculture system. The foundation of a functional installation is the conductor itself, creating the primary interface between the plant and the environment. The protocol specifies the use of pure, uninsulated copper wire to ensure maximum conductivity. The presence of any plastic insulation or synthetic coating acts as a dielectric barrier, effectively blocking the very atmospheric interaction the system seeks to harness. The copper must remain exposed to the air, allowing unimpeded contact with ambient electromagnetic fields. Technicians begin by selecting the appropriate biological support structure. Only healthy, actively growing branches with a diameter between 1 and 2 inches are chosen for the installation. This specific dimensional threshold is critical. A branch narrower than 1 inch may lack the structural integrity to support the coil over a growing season, while a diameter exceeding 2 inches often indicates older, thicker bark that acts as an insulator, dampening the transfer of energy to the cambium layer beneath. Once the host is selected, the copper wire is applied in a specific spiral pattern, a geometry chosen to mimic natural growth ratios found in phyllotaxis, the arrangement of leaves on a stem. This spiral is not merely aesthetic, but serves as a solenoid, a shape known in electrical engineering to concentrate magnetic fields along its axis. Crucially, the application of this coil requires a delicate balance between contact and constriction. The wire must be secure enough to maintain its position against wind and rain, yet loose enough to accommodate the plant's natural expansion. A common failure point in amateur installations is the constriction of the bark, a condition known as girdling. If the wire is wrapped too tightly, it chokes the vascular tissue as the branch widens, cutting off the flow of nutrients and water, effectively strangling the plant the system was meant to aid. To prevent this, A calculated gap is left between the coils, and fasteners such as garden twine are used to secure the structure without applying compressive force to the tissue. Beyond the immediate geometry of the wire, the orientation of the entire apparatus is often debated. While some practitioners align the coil's axis with magnetic north in an attempt to optimize the absorption of geomagnetic fields, this specific practice lacks the rigorous verification found in other steps of the protocol. In more complex soil-based variations, the system incorporates vertical electrodes inserted directly into the ground. These rods, which can be constructed from copper, galvanized steel, or iron, serve to ground the atmospheric charge, completing the circuit between the sky and the soil matrix. A voltmeter is frequently employed to monitor the potential difference, with readings generally maintained between 0.5 and 3 volts. This low voltage parameter is essential, as exceeding this threshold risks damaging the delicate root hairs and microbial life essential for soil health. The installation is not the final step. The system requires continuous maintenance to remain effective. Copper, while highly conductive, is reactive. Over time, exposure to moisture and oxygen leads to oxidation, forming a layer of patina that alters the electrical resistance of the surface. Regular inspection is mandatory to identify signs of corrosion or physical damage. If the conductivity drops due to heavy oxidation, or if the wire becomes frayed, the component functions less as an antenna and more as a resistor, impeding the flow of energy. Technicians must clean or replace worn coils to ensure the system continues to function at optimal capacity. This precise methodology, incorporating material purity, geometric alignment, and ongoing maintenance, distinguishes the verified electroculture system from random experimentation. However, even when these rigorous standards are met, the translation of this engineered precision into consistent harvest data proves far more elusive than the installation itself. The transition from precise installation protocols to verifiable field data reveals a stark divide between theoretical promise and agricultural reality. While anecdotal reports from home gardeners frequently cite tripled yields in massive, unrecognizable vegetables, the rigorous environment of controlled scientific trials presents a far more conservative narrative. The challenge lies in the chaotic nature of biological systems, where isolating the impact of a single copper wire from the myriad of environmental forces becomes a statistical nightmare. A pivotal 2009 study published in the Journal of Agricultural Technology acknowledged this ambiguity directly. Although the researchers observed distinct physiological changes, including a deeper green tint in electrified crops and increased root growth in barley coleoptiles, they could not map the path from cause to effect. They explicitly stated that the mode of action of the current in producing increased growth and yield is still obscure, highlighting a persistent gap in mechanistic clarity. More recent research has attempted to close this gap with high-tech interventions, moving beyond passive copper coils to active energy harvesting. A 2022 study conducted in China and published in the journal Nature Food provided specific metrics for this phenomenon using pea plants. By applying a low-voltage electric field through copper wiring to the soil, the researchers documented a quantifiable acceleration in biological processes. The data showed that seed germination speed increased by approximately 26.3%, while the final pea yield rose by about 17.9%. To achieve this, the study utilized an innovative all-weather triboelectric nanogenerator, or AWTENG, a device designed to convert random environmental energy, such as the friction of wind and the impact of raindrops, into usable electricity for the crop, bridging the gap between these modest laboratory gains and the massive claims of enthusiasts or isolated case studies, such as an Italian farm where a 30% increase in tomato yield was reported within a greenhouse setting. However, even this significant figure pales in comparison to the triple-digit explosions often cited online. The primary difficulty in validating electroculture's effectiveness lies in the inability to isolate the copper variable from confounding factors like soil composition, ambient weather, and existing nutrient levels. In an open garden, a sudden improvement might be attributed to the copper antenna, when in reality, it may stem from a favorable shift in temperature, distinct rainfall patterns, or the specific mineral profile of the local earth. Rigorous trials often fail to replicate the dramatic results seen in uncontrolled settings because they strip away strictly localized conditions that might unknowingly contribute to the success. The disparity suggests that observed benefits may be highly crop-specific or dependent on pre-existing soil deficiencies. Evidence points to the possibility that electroculture acts as a corrective measure rather than a universal booster. If a plot of land suffers from poor ion transport or specific mineral lockup, the introduction of an electric field might liberate those nutrients, resulting in a spike in growth. However, in a balanced, nutrient-rich soil, the same intervention might yield negligible results. This lack of broad applicability is a key reason why the tripling claim remains statistically elusive in professional research journals. Furthermore, scientific scrutiny focuses heavily on the lack of a linear dose-response relationship in yield data. In standard agronomy, adding more fertilizer typically correlates with increased growth up to a saturation point. With electroculture, this linearity breaks down. A stronger current or more copper does not automatically equal a larger harvest. The inconsistent and often modest improvements reported in controlled studies suggest that the technique operates on a delicate threshold. The evidence points to a potential modest effect, a tool for marginal gains rather than a guaranteed agricultural revolution. Yet, while the harvest benefits remain debatable, the physical residue of the system is undeniable. As technicians focus on the potential for immediate abundance above ground, a far more critical accumulation process is silently taking place beneath the surface. A critical examination of long-term soil health reveals that this accumulation introduces a significant environmental risk factor, often overlooked in the pursuit of immediate yield. While the visual indicators of plant growth may appear robust in the short term, the substrate beneath undergoes a fundamental chemical alteration that is often invisible to the naked eye. A comprehensive 12-year field experiment conducted in agricultural soil in New South Wales, Australia, proactively addressed this concern by meticulously examining the long-term consequences of copper exposure. The study involved the application of copper sulfate at a wide range of concentrations, establishing a gradient from 0 to 3,310 milligrams of copper per kilogram of soil. This vast spectrum allowed researchers to pinpoint the precise moment where the soil's biological capacity begins to fail, moving beyond theoretical models to observe the hard limits of the Earth's tolerance. The primary metric for this degradation is substrate-induced respiration. This measurement serves as a critical proxy for the overall biological activity and health of the soil microbiome, effectively quantifying the collective metabolic rate of the bacteria and fungi living underground. In a functional ecosystem, the introduction of a carbon substrate should trigger a rapid increase in respiration, indicating a hungry, active, and responsive microbial community ready to cycle nutrients. However, the New South Wales data indicates that soil functionality remains stable only until copper concentrations hit a specific, unforgiving tipping point. Through detailed soil functionality analyses, researchers discovered that plots receiving 200 milligrams per kilogram of copper or less exhibited soil functionality comparable to control plots. Within this safe zone, the copper acts as a benign presence, effectively invisible to the broader metabolic processes of the soil matrix. Once levels exceed 200 milligrams per kilogram, the longitudinal data reveals a sharp, nonlinear decline in substrate-induced respiration. This is not a subtle reduction, but a systemic collapse of biological activity. The soil, saturated with the metal, loses its ability to process carbon and cycle nutrients effectively, behaving less like a living ecosystem and more like sterile mineral matter. Remarkably, this suppression of functionality persists for over 12 years after the initial exposure. In the study, agricultural soils exposed to concentrations greater than 200 milligrams per kilogram 12 years prior continued to exhibit significantly diminished functionality when compared to control plots. Unlike organic contaminants that break down under UV light or volatile synthetic fertilizers that wash away with the rain, the copper residue remains distinct and chemically active, locking the soil into a state of suspended animation. The findings suggest that copper operates under a deceptive duality. It is not merely a nutrient, but a potential toxicant at high accumulations. The research issues a clear warning that copper concentrations in agricultural soils should not exceed the 200 milligram threshold due to the high probability of significant and lasting functionality loss. This creates a challenging paradox, where an agricultural practice aimed at enhancing plant growth, such as the application of copper-containing compounds or the degradation of copper wires, could inadvertently degrade the very soil ecosystem that sustains them in the long run. The copper does not simply disappear once the harvest is complete. Its effects are cumulative and remarkably persistent. The 200 milligram threshold represents a rigid boundary between biostimulation and environmental toxicity. Below this line, the ecosystem tolerates the input. Above it, the fundamental machinery of the soil grinds to a halt. In many instances, the highly contaminated soils display markedly different microbial community structures, indicating that the original, diverse populations had been wiped out or permanently displaced. Ultimately, the 12-year post-exposure assessment revealed that soils which had surpassed the threshold had not regained their original functionality, proving that the adverse impacts of excessive copper underscore a risk that extends decades into the future. It is a permanent modification of the geology itself, turning fertile ground into a metallic hazard zone where biological life struggles to respire. This degradation, however, is not just a reduction in volume, it is a fundamental alteration of the community architecture itself. The impact of copper loading extends far beyond the simple measurement of general respiration rates. It fundamentally restructures the architecture of the microbial communities living beneath the surface. When copper accumulates in the soil matrix, it forces a radical shift in the subterranean populations of bacteria and fungi, altering the biological engine that drives agricultural productivity. A closer analysis of the data reveals a complex and somewhat deceptive phenomenon regarding biodiversity. In ecological terms, diversity is measured in two distinct ways: alpha diversity, which counts the number of species within a single specific sample, and beta diversity, which measures the variation in species composition between different environments or plots. Under high copper conditions, the study reveals a counterintuitive increase in alpha diversity. At first glance, this metric suggests a thriving, varied ecosystem, as the count of distinct genetic signals within individual soil cores remains high or even rises. However, this localized abundance masks a broader systemic collapse. The critical indicator of health, beta diversity, drops significantly across different plots. This divergence signals a process of homogenization. As the environment becomes saturated with metal, the unique, specialized communities that once varied from one meter to the next are eradicated, replaced by a uniform blanket of survivors. The landscape loses its textural complexity, becoming biologically monotonous. This homogenization occurs because the high copper environment acts as a severe evolutionary filter. Taxa that are naturally tolerant to copper begin to dominate the substrate, aggressively displacing the specialized microbes essential for resilience. These copper-tolerant organisms are often generalists, capable of enduring toxic stress but frequently lacking the nuanced metabolic capabilities required for complex nutrient cycling. The specialized bacteria responsible for fixing nitrogen, decomposing tough organic matter, or solubilizing phosphorus are pushed out, leaving behind a hardier, yet functionally limited, biological workforce. The loss of beta diversity signifies a loss of ecological complexity and functional redundancy within the soil microbiome. When microbial communities across different sites become indistinguishable due to contamination, the intricate networks of interaction that sustain soil health disintegrate. The persistence of high alpha diversity counts alongside this functional collapse is largely attributed to the mechanism of dormancy. Soil microbes possess the evolutionary capacity to enter a state of suspended animation when faced with lethal environmental stress. In this sleeping state, the organism shuts down its metabolic processes to survive, effectively waiting for conditions to improve. Crucially, while these dormant microbes do not contribute to the ecosystem's workload, they do not break down compost or feed root systems. Their DNA remains intact. Sequencing technologies pick up these genetic signals, registering the organism as present. This creates a dangerous illusion of health, where the soil appears strictly biodiverse on a spreadsheet, functions as a sterile medium in practice. This dormancy masks the true extent of the ecological damage until the system is subjected to further stress, at which point the lack of active, functional workers causes a rapid failure. Ultimately, the reduction in beta diversity signals the erosion of the complex networks required for nutrient cycling and decomposition. The soil ecosystem relies on a diverse array of distinct microbial interactions to maintain balance and recover from disturbances such as drought or disease. As the community simplifies and homogenizes, this buffer vanishes. The soil becomes fragile, stripping itself of the internal biological processes that naturally regulate fertility. Consequently, the land ceases to be a self-sustaining system and transforms into a dependent substrate, reliant entirely on exportation. Undermines the long-term sustainability of the agricultural system, creating a paradox where the intervention intended to boost the harvest eventually necessitates a perpetual, costly life support system for the ground itself. The uniform survival of copper-tolerant taxa represents not a triumph of adaptation, but the silence of a once dynamic underground economy. This silence underscores the juxtaposition of Lakhovsky's vintage oscillation theories with modern soil data, revealing a complex trade-off between immediate harvest volume and long-term ecological stability. While the narrative of low-cost copper electroculture is alluring, the invisible cost to subterranean biodiversity is now verifiable through rigorous analysis. Data confirms that copper residue forces a selective pressure on microbial communities, creating a functionality deficit that persists for over 12 years. Once contamination exceeds the critical 200 milligram threshold, future agricultural resilience depends on prioritizing long-term soil functionality over short-term yield spikes. What surprised you the most about the soil data? Let us know in the comments. If you enjoyed this deep dive, don't forget to like, share, and subscribe to the channel.